Models are becoming more and more important in the medical field. They range from models predicting the stress distribution in hip prosthesis to models predicting the spreading of a virus. However, a model is only as good as it predicts reality. So I combined an experimental with a computational analysis to simulate mechanics-induced arterial growth.
Mechanics are present in your whole body, but in my research I focused on the mechanics of your cardiovascular system. Your cardiovascular system is composed of your heart, blood vessels and blood. There are two sides to your heart, the systemic or left side, which pushes the blood from your heart to the rest of your body through the aorta, and the pulmonary or right side, which pushes the blood from your heart to the lungs through the pulmonary artery. As you can imagine, you need more pressure to push the blood from your heart to your whole body than from your heart to your lungs. So the left side of your heart works on a pressure that is up to 7 times higher than the pressure in your right side. Also, to ensure a good blood flow, you have several valves in your heart. You have, for example, the pulmonary valves and the aortic valves.
It can happen that a person's aortic valve loses its function. In that case, the aortic valve needs to be repaired or replaced. When replacing the aortic valve, the surgeon can choose between mechanical valves, donor valves, porcine valves, or the surgeon can take the pulmonary valve of the patient itself. And this is done in the Ross procedure.
In the Ross procedure, the surgeon takes a patient's own pulmonary valve and puts it in aortic position. From that point on, it is called a pulmonary autograft. Where the pulmonary valves were, donor pulmonary valves are placed. But the pressure present in the aorta compared to the pressure in the pulmonary artery is much higher, and the pulmonary autograft experiences a whole new mechanical environment. As arteries are living materials, they have the ability to adapt to a new environment. They can actually grow and remodel, which is a big difference compared to standard engineering materials. But this means that in some patients, the pulmonary autograft remains stable, but in other patients, this pulmonary autograft dilates and continues to dilate until it fails.
My goal was to investigate if we could characterize the changing mechanical behavior of the pulmonary autograft. So we performed a set of animal experiments. In these animal experiments, we placed a piece of pulmonary artery in aortic position for 6 months. Now that piece of pulmonary artery serves as a pulmonary autograft. We mechanically evaluated the arterial tissues at Fiber, an expert center for mechanical evaluation of biological materials and medical devices. To mechanically test arterial tissue, I cut out a square piece of the tissue and mounted in a planar biaxial testing device. Next, the device will pull on the different sides of the sample while tracking the forces. Using speckles, cameras and digital image correlation, I track the deformation of the sample during the test. Using the force and deformation data of the sample, I then calculate the stress strain curve.
After testing all the tissues, we averaged the slopes of the curves. We saw that normal aorta and normal pulmonary artery have distinctively different mechanical behaviors. The aorta, in dark blue and orange, has higher slopes, and the slopes increase faster than the slopes of the pulmonary artery, in yellow. The samples of the pulmonary autograft, so the pulmonary artery that was in aortic position for 6 months, showed something remarkable. We saw that some samples showed normal pulmonary artery behavior. You can see that the light blue bars resemble the yellow bars, whereas others showed aorta-like behavior. The green bars are closer to the blue and orange bars. So some samples were able to adapt to their new environment and act as if they were aorta, whereas others were not.
However, why some samples adapt and others don't was not yet clear. So I turned to computational models, more specifically finite element models. To make a finite element simulation, you need a material description. Generally, arterial tissues are described as hyperelastic materials. This means that their mechanical behavior can be described using a strain energy density function.
A typical strain energy density function for arterial tissue is the Gasser-Ogden-Holzapfel model. The nice thing about this model is that it reflects the arterial microstructure. How is that? Well, an artery can be seen as a fiber-reinforced material. It has an elastin matrix in which collagen fibers are dispersed. The Gasser-Ogden-Holzapfel model reflects this structure, as the first term expresses the matrix contribution and the second term expresses the fiber contribution. Next, to implement growth and remodeling into this equation, I used the constraint mixture theory. This theory states that an artery consists out of different constituents that can have their own material properties, own stress-free state, and own speed of degradation and deposition, but they are constrained to move together. So we adapted the strain energy density function to include all these features. This was not readily available, and we implemented it in the finite element software Abacus using a user material subroutine.
Next, we also needed the geometry and loading conditions. The geometry was taken from MRI images taken right after surgery. The loading conditions, which is the aortic pressure, was measured during surgery. Finally, we had our computational model, and now we let it virtually grow and remodel for 6 months.
What we saw is that if we look at the collagen fraction, it is not completely homogeneous throughout the entire autograft. If we then look at different geometries, we can see that depending on the geometry, it is much more heterogeneous. If we look back at our experiments, the samples we tested were probably coming from different parts of the autograft experiencing a different mechanical environment. So the influence of mechanics on how arteries respond cannot be underestimated.
We could conclude that by combining computational models with experimental data, we could show the applicability of these types of models. And we know that these models will become more and more important in predicting the outcome of a surgical procedure.